In this lecture, we'll be discussing the chemistry of hydrogen. It has a pretty unique chemistry based on its relatively small size compared to everything else. And we'll also be introducing nuclear chemistry. And so on the slide shows a unique nuclear reaction hydrogen can go through, that is nuclear fusion. We won't really be discussing this in too much detail, at least yet. That will probably come next lecture. And then some important nuclear symbols are shown in this table. Right, so chapter 14.1, we'll be bouncing around a little bit now, but chapter 14 is where we go through and sort of survey the different families in the periodic table. But we're going to start with hydrogen in section 14.1 and talk a little bit about it first. Towards the end of the quarters, when we'll go through and survey the rest of the families. Okay, but we're going to first start with talking about hydrogen and talking about nuclear chemistry. Okay, so hydrogen, it's very simple structure. The nucleus is only one proton. Okay, there's no neutrons, and then it only has one electron. Okay. It's the most abundant element in the universe. Okay, so it's the simplest. It was the easiest thing produced from the Big Bang. Okay, and so it's by far the most abundant element in the universe. Okay. It exists in nature as a diatomic gas, H2. Okay. And H2 is colorless, it's odorless, very low melting point and boiling points. So it was, actually probably a pretty hard element to discover in a sense. Okay. It's abundant, though, in combination with other elements, especially with oxygen on this planet as H2O or water. Okay. Where it belongs in the periodic table is sort of up for debate, and that is because it shows some similar reactivities with a number of different groups. And one of those places, and where it's typically placed, is with the group 1 metals, the alkali metals. And that's because of the electron configuration, right? It has one s electron. And so all of these have valence electron configurations with one s electron. So that's why it's generally put there, but it's not a metal really, right? It's not solid, it's a gas. So does it really belong there? We can put it in the halogens, so over column 17 or the 7A family in the old nomenclature. So you could put it there because it is a gas. It exists as a diatomic gas naturally, like the other halogens like F2, Cl2 exist. And it reacts in a similar fashion. It reacts with other things and forms one bond. Okay, so that's also very similar. And then some people even think that you can put it above carbon, just based on some other reactivities with it, and the fact that its electronegativity is sort of similar to carbon, and it does readily form bonds with carbon. But there are multiple places that you could put it, and it'd be fairly it would make sense. Okay. Like group 1A elements, hydrogen, again, it has that same electron configuration. And it has a very common oxidation state to those alkali metals, a +1 oxidation state. It can readily give up that electron and become just a proton. Okay. Unlike the metals, though, hydrogen shares electrons with nonmetals rather than just transferring them to them. So that's one way it differs. Okay, and then it has a much higher ionization energy than any of the alkali metals, just due to its small size. So there's some similarities with those group 1 elements, and there's some differences. Okay, if we compare that to carbon, the group 4A or elements, the similar chemistry will come from the fact that hydrogen has a half-filled valence level, and so does the carbon group. Hydrogen also is similar to other group 4A elements in terms of ionization energy, electron affinity, electronegativity, and bond energies. Okay. All right, and we've discussed this as well, like the halogens. It exists as a diatomic molecule. It needs only one electron to fill its valence shell. Unlike the halogens, hydrogen is much lower in electronegativity than any halogen, right? And you remember the atomic trend as the electronegativities is always increasing as you go to fluorine. So if you put hydrogen above that, that kind of bucks that trend. Hydrogen lacks the 3 valence lone electron pairs that halogens have. So it doesn't have the lone pairs. Halide ions, X- ions, are common and stable, but a hydride ion, H- is very rare and it's very reactive. Okay, so you can see that hydrogen kind of fits in many different places, but it also is a little bit of an outcast as well. All right, we look at some ionic and covalent hydrides. So ionic or salt-like hydrides form when hydrogen reacts with very reactive metals. These hydrides are white crystalline solids, so things like lithium or calcium, hydrides, so bonding with hydrogen. These are ionic or salt-like. It can also form covalent or molecular hydrides, so that's when hydrogen reacts with nonmetals. In most covalent hydrides, hydrogen has an oxidation number of +1. I can't think of an example of it where it has anything other than an oxidation number of +1. But I'm sure there are probably other examples in covalent hydrides. Okay. So something like fluorine mixing with hydrogen, you get HF. That's a covalent hydride. Okay, the metallic hydrides, the salt-like hydrides, can form with transition metals as well. Okay, so you can have a transition metal and hydrogen and sort of mix a mixture of them. Okay. And in these cases, you also have not just hydrogen, but also H2 molecules, along with the hydrogen atoms occupying the holes in the crystal structure of the metal. And the hydrogen has been kind of thought of as a possible future fuel because it breaking that bond and burning it to convert to H2O. One, that's a very clean byproduct, and two, it's a very energetic bond to break, so a lot of energy comes out. One problem is though storing enough hydrogen gas. It's so small that it can diffuse through lots of different things, and so one thought of as a way to store hydrogen is in sort of metal matrices like this, where the hydrogen gas can kind of like get stuck in a metal crystal structure. Okay. Hydrogen, most abundant element of the universe again. In the early universe, it was too hot for atoms to form, okay, only small nuclei. And it was only when the universe cooled could nuclei capture electrons to form atoms. At that time, the universe was about 92% hydrogen, it's estimated, and 8% helium. By numbers of atom, or 75 and 25% by mass, with trace amounts of lithium and beryllium, but really not much else. Okay, the universe is still estimated to be about 90% hydrogen. Okay, as the universe has cooled further, it's allowed stars to form. Hydrogen is the ultimate source of all the other elements through nuclear fusion in the stars. Okay. So how is the sun powered? Well, stars, for their lives, stars fuse elemental hydrogen into helium. So two hydrogen atoms under very intense pressures and temperatures can collide together and be pressed together in such a way that they actually fuse. Okay. And when they do that, one of the nuclei of these two hydrogens, they come together, the two protons. And one of the protons will be converted into a neutron, and thus forming what's known as deuterium, which here is abbreviated with a 2, meaning it has an atomic weight of 2 now, but it is still hydrogen, technically, because it still only has one proton. Okay, when it does this, not that you probably don't need to know this part, but it produces a positron as when the one proton is converted into a neutron. That's part of the nuclear reaction there. Then the deuterium and another hydrogen can fuse again. This produces a gamma ray, and you get 2 protons and 1 neutron, which would be a helium-3 nuclei, and 2 of these can now fuse together. When that happens, you lose 2 hydrogens, and you're left with a helium. So you have more hydrogens now that can combine again to form the process all over again. So this is a big kind of chain reaction that's going on in stars. It's estimated these reactions are about 85% of the sun's energy. The remaining 15% comes from reactions that produce elements like beryllium and lithium. This whole thing's producing neutrinos, gamma rays, X-rays, UV, visible light, IR light, so tons and tons of light. What about the other elements? Well, the star, when the star's core runs out of hydrogen, the star begins to die out, okay? And then the stars undergo different fates depending on how big they are. Okay? They can form into something that's known as a red giant, and then it becomes to manufacture heavier atoms like carbon by fusing the helium atoms together. More massive stars begin a further series of nuclear burning or reaction stages. And elements formed in these stars range from oxygen throughout to iron. And so that's all well and good. You can produce these in stars, but how do you get them on a planet? Well, you have to have a star that's ultimate fate is becoming a supernova. And when a star is a supernova, it essentially explodes. And when it explodes out, all the elements that it has been making over the years and years and years of its life just get shot out into space. Okay, and then those can be captured by other stars, and again, nuclear fusion can go on making elements, or they can collectively sort of collect into sort of dust and debris and eventually form planets. Okay. After a star becomes a supernova, you get what's left is a neutron star, where that core implodes to form a neutron star, which is thought of essentially as like a big nucleus, a very, very compact, dense entity in space. Only 90 of the 116 known elements occur naturally. So where do the other 26 come from? And the answer to that is found in the development of nuclear power plant and machines known as particle accelerators. So the 90 natural elements can occur from, the stars making them, and the other ones that we know of, that we found, have all been man-made. We can write the nuclear chemistry, or the fusion of hydrogen to form helium, in some reactions. Okay, and you write the atomic symbol, and then the top number up here is the mass number. Okay. The bottom number here is the atomic number, so that's the number of protons. So the number of protons plus the number of neutrons equals that mass number. And then you'll see different symbols here. So this is a beta. That means that's a particle now, and it has a 0 mass, has 1 proton. So that is a positron. You have a gamma, so that's just energy. It does not have the mass numbers. What else do we have? So in our reaction sequence, we have 2 hydrogens fusing together to form H2 and that positron. You have the deuterium now, the H2 fusing with another hydrogen to form helium-3 and that gamma ray. Then helium-2, helium-3s can form together to form that helium-4 and 2 more hydrogens. What you'll notice here is these numbers add up to each other. So 1 plus 1 equals 2 plus 0. 1 plus 1 equals 1 plus 1. Okay, 2 plus 1 equals 3 plus 0. And 1 plus 1 equals 2 plus 0. So those numbers have to add up on both sides of the arrow. Right, and this, the reaction all have energy coming out, and there's this relationship that tells you, how much energy, right, for mass, and even, a small mass can give you lots of energy, right, because you're multiplying by the speed of light squared. Right, there's 3 isotopes of hydrogen. These elements occur in nature as a mix of isotopes. So in hydrogen, we have the I guess what's called protium, although I've never really heard of it called that, but that's the typical hydrogen. Hydrogen with a mass number of 2, so having 1 neutron, 1 proton, that would be deuterium, and hydrogen with a mass number of 3, so now it has 2 neutrons and 1 proton. That is called tritium. And their mass units are shown. Basically, they're 1, 2, and 3, although there's a little bit, if you're going down in significant figures, showing more significant figures, you're going to have some decimal place there, but essentially they're 1, 2, and 3. The natural abundance, almost 100% in the mass number of 1, but there is a little bit, about 1% naturally of deuterium, and then tritium naturally is almost non-existent. Okay, but there's very, very small trace amounts of it. Okay, half-life in years, the first 2 are stable. Tritium is radioactive, and that is 12.32 years of a half-life. Okay. The boiling points are shown, very similar chemical properties, and the melting points, although don't really need to don't typically need to consider the melting or boiling point of well, we know it for water, so these are of the hydrogen, deuterium, or tritium as H2O, D2O, or T2O. Okay, and they're fairly similar here, right? Deuterium is just very slightly higher melting and boiling point. Tritium's slightly higher melting point, but the boiling point has not been determined. Right. Nuclear reactions, like chemical reactions, are accompanied by changes in energy. The energy changes in nuclear reactions are much greater than the chemical reactions. What about the conservation of mass? Right, that E equals mc squared. That tells you a little bit is that what it tells you is that energy and mass can be converted. So the mass of an atom is always less than the sum of the other masses of its component particles. Only exception is hydrogen, and this is what's known as the mass defect. The amount of energy released when a nucleus forms is the nuclear binding energy. So that's another concept, is that when a nucleus forms, there's this nuclear binding energy that's actually released. So if we look at the subatomic particles, protons, neutrons, and electrons, their charges are shown here. In terms of electric charge, we have a proton as a plus 1.6 times 10 to the 19th coulombs, and electrons the same magnitude but negative. We just call that the atomic charge. We just call this as a plus 1 atomic charge, and an electron is a minus 1. Okay, but in the unit of coulombs, this is what that would be. And neutrons are neutral, so they're zeros. Okay, the masses, proton and neutron are all pretty similar in masses. The electron is smaller by about 3 or 4 orders of magnitude. Right. So our atomic mass, we just assign basically a 1 to a proton and a 1 to a neutron, although there's 0.0073 and 0.0078 at the end of it. But essentially they're 1. And what an electron would be in atomic mass units is shown here. And so that's why we really don't take these into account in atoms when we're calculating atomic weights or molecular weights, is because you need many, many, many electrons to even add up into one mass unit. Okay, and all of these have spin to them, and the spin is 1/2. Okay. All right, so if we look at our first reaction here, hydrogen plus hydrogen going to deuterium plus that particle and energy, and we look at the energy in terms of E equals mc squared. So because of hydrogen, the fact that it only has 1 proton in its nucleus, there's no mass defect from binding of other nuclear particles. So its mass defect is 0. When we get to deuterium now, then there's a neutron, right? And that's when you get some mass defect. But for this class, it's probably a little bit over our head there. If you wanted to calculate, just how much energy a particle would have, something like a hydrogen could have, you could take this formula here and plug in the mass of one of a proton, for example, in would it be kilograms? Yeah, it'd be kilograms. And then the speed of light, which is 3 times 10 to the 8th meters per second squared, and you'd get an estimate of the number that one hydrogen molecule contains. Okay, so moving to talk about radioactive decay and nuclear stability, these are material from chapter 24 of the book. So we're bouncing from chapter 14, section 1 to chapter 24. So components of the nucleus. We've talked a little bit in the hydrogen section about the concept of nuclear fusion, some nuclear reactions, but hopefully it makes a little bit more sense now when we're covering chapter 24. We'll talk about actually all the components of the nucleus in some more detail. Okay, most of the mass of an atom is concentrated in the dense, tiny nucleus. Okay, so that's sort of review from the first quarter of general chemistry. In a sense, all of that mass in an atom is that, and it's been kind of an estimation or a visual aid of an atom is if you have a basketball at the center court of a basketball arena, that basketball would represent the size of the nucleus, and the basketball arena represents the size of the atom, so the electron cloud around that atom. So you see that most of the mass is in that very small nucleus, and the rest of the atom, in a sense, is mainly just kind of air. Nucleus comprises of neutrons and protons. Okay? Actively, they're called nucleons because they're members of the nucleus. The total number of nucleons gives the mass number. Okay, and that's the number that's up, the superscript that precedes the letter of the element. Okay. An atom with a particular number of protons and neutrons is called a nuclide. Right? So something that has a set number of protons and neutrons just referred to as a nuclide. The number of protons defines the identity of the atom. So that for a particular atom, the number of protons doesn't change. If that number changes, it's a different element. Okay. An isotope is one of two or more nuclides that have the same number of protons but a different number of neutrons. Okay, so the number of neutrons in elements can change. Okay. And that gives you a different mass number for that element. So the notation here, X is that atomic symbol, A is the mass number. The mass number is protons plus neutrons. Z is the protons, that's the proton number. You can also think of it as the charge. So for example, if we wanted to write an electron, so if we're talking about particles now, subatomic particles, the X now is not going to be the chemical symbol on the periodic table. The X now will be, for an electron, it will be a lowercase e. Proton is a lowercase p, and neutron is a lowercase n. Okay. Electrons don't have any mass to them. Well, they do have a small amount, but we just kind of round that to 0 for their symbol. And it has a -1 charge, so that goes in the subscript that precedes the symbol. Protons have one mass unit, right, one proton, and they also have one positive charge. Right? And then neutrons are one mass unit, but 0 charge. Okay, so here's a comparison of what to do with chemical reactions and nuclear reactions. In a chemical reaction, one substance is converted to another, but atoms never change their identity. In nuclear reactions, atoms of one element are typically converted into atoms of another element. So nuclear reactions, the atom, what the atom is changing. Okay. In chemical reactions, electrons and orbitals are involved as bonds break and form, but the nuclear particles don't take place in those reactions. And that's the opposite in nuclear reactions. That's what's reacting are the protons and neutrons, and other subatomic particles are involved in these. Electrons and orbitals take part in this much less often. So the electrons that are in the orbitals of these atoms are not really taking place in the nuclear reaction. Reactions are accompanied by relatively small changes in energy and no measurable changes in mass. Okay, so there's mass conservation in chemical reactions. On the other hand, nuclear reactions, they have very large changes in energy and measurable changes in mass as well. And so that kind of goes against that first law, mass conservation, right? Does not apply to nuclear reactions. Chemical reaction rates are influenced by temperature, by concentration, catalysts, and compound in which the element occurs. Reaction rates of nuclear reactions depend on the number of nuclei, but are not affected by temperature, by catalysts, or except on rare occasions, the compound in which an element occurs. Okay, but you can really kind of think in this class, they don't depend on the same things that the chemical reactions are dependent on. So what types of nuclear reactions are there? Both chemical and nuclear reactions take place because they're going to be going to a more stable state. So we can have nuclear fusion, and this is a case where two lighter nuclei collide to form a heavier nucleus. And we saw that as an example in hydrogen, and stars can undergo that. There's also nuclear fission. So fusion, two things coming together. Fission is where you have a heavier nuclei that breaks up to form two lighter nuclei. Okay, so that's nuclear fission. And then you can also have nuclear decay, and that's when a unstable nucleus decomposes to form a more stable nucleus. Okay. And in both cases, you have the reactants equaling the products, so the total A and total Z of the reactants has to equal the total A and total Z of the products. Okay. All right, so nuclear equation. Okay, when a nuclide decays, it forms a daughter nuclide of lower energy. The excess energy is carried off by the emitted radiation and the recoiling nucleus of the daughter nuclide. Okay. The decay process is represented by a balanced nuclear equation. Both the total charge and the total mass must be balanced. Okay, so that's what the total A and total Z, that's what that means. Those have to be balanced. Okay, stability, two key factors determine the stability of a nuclide: the number of neutrons and the number of protons, and their ratio, that's one, and the total mass of the nuclide. Okay. If you plot the number of neutrons versus the number of protons for all stable nuclides, that produces a band of stability that gradually curves above the line for n equals z. Okay. So that neutrons equals protons. That's kind of where that stability starts, and then you'll see it kind of curving where you get more neutrons are needed for stability. Okay, so lighter nuclides are stable when that n equals z. As z increases, the n to z ratio for stable nuclei gradually increases. All nuclides with a z greater than 83, all of them are unstable. Okay, so here is that stability. If you plot that out, what you'll see here, though, is this line is just the n to z ratio of 1. So you see they start out, the stability is kind of following that line, but as you go heavier and heavier, you're now requiring more neutrons compared to the proton number. So the modes of radioactive decay. The first mode we'll talk about is alpha decay, and it's abbreviated with the Greek symbol alpha. This involves the loss of what's known as an alpha particle from the nucleus. Each alpha particle emitted, a decrease by 4. A is decreasing by 4, so that would be the mass number decreases by 4. And Z, the charge or number of protons, decreases by 2 in the daughter nuclide. So this is the most common form of decay for heavy unstable nucleus. So here if we have radium that has a mass number of 226 and it decays into radon, right? It mass number now drops by 4 and the number of protons or atomic number is dropping to by 2. Okay, so that's what an alpha particle consists of. And actually the alpha particle is consisting of 2 protons and 2 neutrons. So essentially the alpha particle is a helium, the nuclei from a helium atom. Okay. The next form of decay we'll talk about is beta decay, and that involves the ejection of a beta particle from the nucleus. A neutron is converted to a proton, which remains in the nucleus, and a beta particle is expelled. So a neutron can go to a proton, and when that happens, right, you're changing the charge of that neutron to a positive for the proton. So to balance that, right, because both sides of the arrow, that number, that Z number there has to be balanced. So to balance that, a beta particle is created. And that particle has a 0 mass unit, but a -1, right, for that Z value. So if you add up the Z values here, they add up to 0. Okay. Right, A remains the same in the daughter nuclide, but Z increases by 1 unit. So we have, in this case, this is where we get in nickel. So let's look at nickel 63. It can turn into copper 63 by undergoing beta ejection or beta decay. Right. You can also have what's known as positron emission. So a positron is very similar to, and I should mention too, that a beta particle is essentially the same thing as an electron. Okay. Positrons now are the positive charged form of a beta particle. And it's technically the antiparticle of an electron. So if a positron and an electron combine, they will annihilate each other and produce energy. Okay. Proton in the nucleus is converted into a neutron and a positron is emitted. So that's where the positron emission comes from. So now instead of neutron going to proton, we have a proton going to neutron. Okay, and that would elicit the release of that positron. Okay. And the symbol again is beta. Okay, so resist the urge to call this a beta particle because it's +1 down here and not a -1. So we call this a positron. Okay. A again remains the same in the daughter nuclide, so it's staying at 11, but the Z is going now from 6 to 5. So you're changing different elements in the other direction. You're getting to a lighter element. Whereas in beta decay, you went to a heavier element. You can get what's known as electron capture. So this, in a sense, is not a decay, but it's the opposite. You're capturing an electron, which is a beta particle. And when that happens, a proton can be converted to a neutron, right? If you have a proton and that nuclei captures an electron, that proton now can convert into a neutron. Okay, so let's try some practice with this. write the equation for the alpha decay of thorium-232. Okay, so for thorium-232, if we look in the periodic table, symbols, it's a 2. Symbol is TH. 90 is the atomic number, so you have 90 protons. And we're told here that the mass number is 232. Okay, so when this decays, we're told it's alpha decay. So for this class, I'm either going to tell you what type of decay it is, or I would show you what element it, like on an exam, what element it has transmutated into, and then from there you could figure out what particle was ejected or absorbed, and thus what kind of radiation or decay it undergoes. I'm not going to expect, in other words, I'm not going to expect you to know that, oh, thorium-232 is an alpha emitter, so you don't have to memorize that. Okay, so what does this change into? Well, 90, we're going to have to subtract 2 from that because that's what the alpha particle has for its number of protons. So now we have 88 protons. If we have 88, looking at the periodic table, that is radium. And if we have 232 mass number to start, and we've lost 4 from that, that would be 228. Right, so that would be the alpha decay of thorium-232. So you release alpha particle and energy, and by doing that, you've converted thorium to radium. Okay, now let's look at the beta decay of xenon-133. So xenon, in the periodic table, the atomic number is 54, so that's the number of protons. And we have a mass number of 133. If you undergo beta decay, where particle has 0 mass and a -1 for that value there, right? You can, since they're the same, you can technically call this an electron as well, although when we're talking about radiochemistry and radioactivity, we generally label this as a beta particle. Right, let's just say energy 2. Right, so what does this become? Well, the A number, the mass number, is not going to change. That's going to stay at 133. The number of protons will, but instead of going down like in the last example, we have a -1 over here. So this one has to be a little bit higher, 1 higher, so that those two add up to 54 on the other side of the arrow. Okay, so that changes the element to something heavier, 1 heavier, which would be cesium. Okay, and then their last, write the equation for krypton-76 undergoing electron capture. So krypton-76, krypton's atomic number is 36, and it's not K, it's Kr. And that's capturing an electron, okay, which we could also write as a beta particle. And what does it go to? Well, 76 plus 0 would be 76. And 36 minus 1 would be 35. So this would be bromine. Okay. There are other types of emission, gamma emission, that involves radiation of high energy gamma photons. So you can kind of think of this more, less like a particle, more like light in a sense, very, very high energy light. It usually occurs together with other forms of radioactive decay. Several gamma photons of different energy can be emitted from an excited nucleus as it returns to the ground state. And gamma emission results in no change in either the A number or the Z number, since gamma rays have no mass or charge to them. Okay, moving on to section 2, the kinetics of radioactive decay. And in this section, we'll go through some of the mathematical calculations that you can do in radiochemistry or radioactive chemistry. So what you typically use in a lab that you do this is something called an ionization counter, and there are different types of these that can detect radioactive emissions as they ionize a gas that's in the detector. Okay, ionization produces free electrons, and gaseous cations. Those are then attracted to electrodes, and they produce a current, which on most devices kind of ends in like a blip or a count. Okay. You have very big instruments in labs called scintillation counters. These detect radioactive emissions by their ability to excite atoms and cause them to emit light. Radioactive particles strike a light-emitting substance, which then emits photons of light, and those photons strike a cathode and produce an electrocurrent that way. So you have this machine that your sample goes into the dark in the machine, and then it's counting the amount of light that it's producing and telling you how much radiation is in there. Right, so the handheld instruments, like a Geiger counter shown here, and this would be, kind of that example of the first sort of example where you have a radioactive sample. If some of the particle that's emitted from that goes into this chamber here that has argon and methane in it, mixture of that gas, you can get an electron being knocked off argon, and that will then move towards the different poles. So here would be a positive pole running down the middle, and the negative charge would be along the sides of the chamber there. And then when that happens, you get a kind of a blip on your amplifier every time that happens. And so you can take this and you can kind of point it at surfaces that you want to see if they're contaminated or not. That's typically how one of these is used. Right, their units for radioactive decay, at least the SI unit, is the becquerel, which is abbreviated capital B, small q. It's defined as 1 disintegration per second, or D per S. So D standing for disintegration per second. Right, the other unit is the Curie, capital C, small I. This is a more commonly used unit. 1 Curie is just defined as 3.7 times 10 to the 10th disintegrations per second. And we can think of radioactivity in terms of a rate. Okay, something more radioactive, the rate is going to be higher. Okay. And all nuclei, the different nuclei decay at a characteristic rate. So you're not going to have a carbon, a specific isotope of carbon like C14 carbon, and find one sample of it decaying at a different rate than another. So every nuclei has its own characteristic rate at which it decays, every radioactive nuclei, that is. Okay. The rate of radioactive decay, A, is also called the activity. Right? And this proportional to the number of nuclei present. Okay? That's the only thing it depends on. It doesn't depend on how that element is bonded into a molecule. That has nothing to do with it. Just how many of those radioactive nuclei are present. So that radioactive rate or activity A is equal to K, a constant, rate constant, times N. Okay, and N is just representing the number of nuclei present. Right. So it follows what's known as first order kinetics, and the rate constant K is called the decay constant. The larger value of decay, the higher the activity of the substance, right? The higher this value gets, the higher that value will be for a given value of N. Okay, so let's try a question using this principle. A sample of 2.6 times 10 to the minus 12 moles of antimony 122 emits 2.76 times 10 to the 8 beta particles per minute. Calculate the specific activity of the sample in Curie per gram. And then the second part, find the decay constant for antimony 122. Okay, so for part A, first we're going to need to convert that number of moles they gave us into a mass. So we had 2.6 times 10 to the minus 12 moles. We need to, atomic weight is given in a sense because that is the weight, the mass number right there, 122. So we have 122 grams per mole. And this would be 3.2 times 10 to the minus 10 grams. Okay. So now we need to, so that's part of it, right? We're looking for grams and part of it. The next part is that we're trying to convert into Curies. Okay. And we're given disintegrations per second. Just disintegrations per minute. Okay. And our conversion factor for Curies, if you remember, is 1 Curie is 3.7 times 10 to the 10th disintegrations per second. So we're going to have to convert disintegrations per minute that were given into disintegrations per second. So 4.6. Oh, excuse me. Jumped ahead. 2.76 times 10 to the 8th disintegrations per minute. Multiply that by 1 minute over 60 seconds. So we're dividing by 60. And what we get is 4.6 times 10 to the 6 disintegrations per second. Okay, that number now we can then take and multiply by our conversion factor. 1 Curie equals 3.7 times 10 to the 10th disintegrations per second. So we have 1.24 times 10 to the minus 4 Curies. Okay, but we're interested in Curies per gram, the activity expressed in Curies per gram. So if we take the number of Curies divided by our mass that we calculated above, 3.2 times 10 to the minus 10 grams, we get 3.9 times 10 to the 5th Curies per gram. Okay, so that's just kind of a unit conversion dimensional analysis type of a problem. And on exams, again, you're given conversion factors you need and the equations. Typically, an equation like this, though, there's no real set equation for it necessarily, so you'd have to be able to use your conversion factors to convert from disintegrations per minute into Curies. Okay, part B, this is an example of a place you would receive an equation on an exam. Right, you have the activity equals K times N. Right? We're trying to solve for our K value though, so let's rearrange this. K equals A divided by N. Right, and so A is the activity which we calculated, or which was given to us above in atoms per minute. So we can go back to that form of it, 2.76 times 10 to the 8th disintegrations per minute. And N is going to be the number of atoms that we have. We're given the number of moles. So that's the number of moles, and we just need to then multiply by Avogadro's number. And, maybe atoms isn't the correct term because it's technically the nuclei that we care about, but, same number. And this would be 1.8. 1.8 times 10 to the minus 4 per minute. Okay, because your number of moles cancels, and you have your atoms and disintegrations, in a sense, are the same thing. So you're getting a per minute because it's a first order reaction. The next thing we'll kind of discuss here in terms of radioactivity is a half-life. Okay? And you probably mentioned this in kinetics in the second quarter of general chemistry. Half-life for a radioactive decay is when half of the nuclei remain, or half of the nuclei in this sample have decayed, depending on how you look at it. Okay. Okay. The number of nuclei remaining is going to be halved after each half-life, and the mass of the parent nuclide decreases while the mass of the daughter nuclide increases. Activity is halved with each succeeding half-life. And the expressions for half-life are shown. Right? We have the ln of the number of nucleides or nucleuses at time t over the number at the start equals minus k times t. Or you can rearrange this to solve for the number at a specific time. It's going to be the number that you started with times e to the k, minus kt. And you can also flip the ratio here. Instead of nt over n naught, you can do n naught over nt, and that would then equal kt instead of negative kt. So by flipping these, you remove that negative sign, in a sense. So that's three ways of representing the same equation. Okay, so here we have a half-life. All right, so starting the number of nucleides that we started with. We go down one half-life, and we're now at half the amount we started with. So in this case, C14 nuclei, right? We start with and not go one half-life. After one half-life here, which is 5,730 years for C14, we have half of what we started with. Then we wait another half-life, so that would be a total of 11,460 years. Now we have 1/4 of what we started with. So 1/2 times 1/2 is 1/4. Right? And then after 3 half-lives, right, we'd have 1/2 times 1/2 times 1/2, which would be 1/8. Okay, so you can see that each successive half-life, you're starting with less, so you're losing less and less each time. You're losing 1/2 of what you're starting with, but it's going to be a smaller number each time. It gets smaller and smaller and smaller. Okay. You can represent the half-life for a first-order process, in that equation is going to be the ln of 2 over k, whatever that rate is. Okay, so it does not, the half-life does not depend on the starting concentration. And we can find the number of radioactive nuclei. Let's try a problem using that concept. In some ways, radioactivity is a little bit easier to deal with than kinetics, because we're just using first order processes, so the number of equations you have to be familiar with is not as much, but some of the math that you'd have to do is still somewhat in depth. So let's work through a problem. Strontium-90 is a radioactive byproduct of nuclear reactors that behaves biologically like calcium, the element above it in group 2A. When strontium-90 is ingested by mammals, it's found in their milk and eventually in the bones of those drinking the milk. If the sample of strontium-90 has an activity of 1.2 times 10 to the 12th disintegrations per second, what are the activity and the fraction of nuclei that have decayed after 59 years? And then it gives us the half-life is 29 years. Okay, so this is strontium-90 is considered one of the bad byproducts of nuclear technology, nuclear reactors or nuclear weapons, because it can be uptaken into the bones of humans, and thus cause bad effects such as cancer later on. So let's try answering this question. Let's work through this. So we were given, let's see, what were we given? To be 1.2 times 10 to the 12th disintegrations per second. The half-life we were given as 29 years. Okay, so then we can find the K value. We'll need the K value, the rate. So the easy way to find that would be using the half-life equation. So half-life equals ln of 2 over K. Right, we can solve that for K. K is going to equal ln of 2 over the half-life. And ln of 2 is just 0.693. Half-life was 29 years. So we get, for the rate, 0.024. And years to the -1, or inverse years, would be the units on that one. Okay, so next, let us use our equation, ln of n at time t over n at 0 equals ln of a0 over at equals negative KT. And so ln of A0 minus ln of AT equals KT. Rearrange this to be ln of AT equals minus KT plus ln of A naught, since we know A naught. So now we know everything on both sides, or excuse me, on the right side. So let's plug values in. So negative K 0.024, 1 over years, times T, which would be at 59 years, plus ln of A naught, which would be 1.2 times 10 to the 12th disintegrations per second. So we've taken the equation here, normally talks about the number of nuclei, and changed it to talk about the activities. Okay. So that's we kind of substituted A in for N there. So this was something like negative 1.4 plus 27.81. So that means the ln of A at time t equals 26.4. And we can solve that A t value is just going to be, if we take e to the exponent of both sides, e to the 26.4, that would be 2.9 times 10 to the 11th disintegrations per second for units. Okay. So now we can take, what fraction of that, what is the fraction of that from what we started at. So if we just take A naught minus A at times t divided by A naught, what we started at, what's that fraction? So we started 1.2 times 10 to the 12th minus 2.9 times 10 to the 11th divided by 1.2 times 10 to the 12th, right? What we started at. That's something like 0.76, so, or 76% of that activity. Okay, so hopefully that's a good start. Next lecture we'll be continuing on with chapter 24 and nuclear chemistry.